Good morning, everyone. So today I want to go through sort of a review of the atomic structure notes, at the same time introducing you to some of the material, especially about protons, neutrons, and electrons, that you can figure out from the periodic table. We're not looking at the periodic table itself per se. That'll be next week or the week after vacation. But I just wanted to go through this so you know how to do this. So we're going to look at an individual square of the periodic table, which we call an elementile. So I've chosen boron for no particular reason. So we're going to take a look at that. So I pulled that out of the periodic table. Now we're going to look at all the different parts. So in this particular case, the name of the element is there, which is fabulous, but it doesn't happen on every periodic table you'll ever see. However, the next thing, this number always, always, always shows up on the periodic table, and that's called the atomic number. The atomic number always tells you the number of protons in that atom. Okay, always, that's what it does. Sometimes it can tell you the number of electrons, but only if the atom is neutral. So you can't really rely on the atomic number to tell you the number of electrons unless you know for sure that it's neutral. All right. That's the chemical symbol. Now, the thing with chemical symbols is they are always capital letters. Always. Sometimes it makes sense, like boron is a capital B, right? That makes great sense. However, something like mercury is capital H lowercase g. Well, where does that come from? It's probably some sort of Latin name. At least that's what it usually is. So anyway, so that's the chemical symbol. So now it's either a capital letter or a capital and a small letter. So if you look over here, you can see C lowercase o is for cobalt, which, which is not the same thing as carbon monoxide, which is capital C, capital O. So especially for those of you who always write in caps, it's not going to work here because you have to indicate that second letter as a lowercase. Okay, so that's that. Then down at the bottom, you have this other number that's always a decimal, always. If you go up to some of the man-made elements, it's not a decimal, but we're not concerned with those at all at this point. And this is called the atomic mass. Now, the thing that I want you to notice is that this atomic number starts with the word atomic, and atomic mass starts with the word atomic, and both of these show up on the periodic table. Okay? Depending on what periodic table you're looking at, it may be that there are additional numbers depending on how complex the table is, but always, 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 you find at least these three things: atomic number, symbol, and atomic mass. So what is atomic mass? Well, it's the average mass of all isotopes of the atom in a sample. An isotope. I think that was on the atomic structure video. I'm almost sure it was. But it's a concept that some people find really, really confusing. So I'm going to try to explain it as best I can. It's not really that bad. So we'll see how it goes. And you can certainly ask me questions about isotopes, but we'll get back to that. So the last number you need to know is this, or the last part of this you need to know is atomic mass. Let me back up. The last thing you need to know about this is something called the mass number. Now, the mass number does not, and sometimes I guess it can, but it does not show up on the periodic table that you're going to be using in class. So let's talk about what that means. It's not shown on the periodic table. Sometimes it is not in here. In order to get the mass number, you look at the atomic mass and you round it to the nearest whole number. So the atomic mass of boron is 11. It's as simple as that. Make sure you're round, if it's a 10.8, we're going to round up to 11. If it was a 10.4, we would round down to 10. So if it's something like 10.5, the 0.5 always rounds up. There seems to be some confusion with that too. Apparently different teachers have taught it in a different way. So if it's a 5, you round up. If it's a 5 or higher, you round up, all right? So what the mass number tells you is the number of protons and neutrons in the most common isotope of whatever it is you're talking about. So there's that word isotope again. We'll get to it in a second. Keep this in mind, right? So the atomic mass is 10.811. And mass number is the number of protons. Shoot, wish that didn't do that. The number of protons and neutrons in the most common isotope. So if it's protons plus neutrons, the mass number, you can't have a decimal because you can't have a piece of a proton or a piece of a neutron. So mass number is always a whole number, and it always means the number of protons plus neutrons. The fact that it's in the most common isotope is not something we really need to worry about, but anyway, let's move on and see what's happening next. All right, so let's look at calculating the number of neutrons. As protons are given to you right on the periodic table with the atomic number. The electrons, either they're the same number of protons or that number of protons if it's a neutral atom, and if it's not neutral, you will have been able to figure out how many electrons it either gained or lost. So let's look at the number of neutrons. So I just picked up argon here. So argon has an atomic number of 18, which means it has 18 protons. Looking down at the atomic mass is 39.948. So by the way, the units on that number are things called atomic mass units, ATMs. And an atomic mass unit is, for all intents and purposes, is the mass of one proton and one electron. It's a little bit more complicated than that, but that's as far as we need to go. So the atomic mass is 39.948, which means the mass number is going to be 40 because you round that number up. Okay, so now we have all the numbers we need. The number of neutrons is calculated this way. The neutrons is equal to the mass number minus the atomic number, or because we know atomic number is number of protons, neutrons is mass number minus number of protons. They're identical formulae, so you can choose either one. So the neutrons is equal to 40, which is the mass number that we just looked at, minus 18, which is the atomic number, our number of protons, and so we know that there are 22 neutrons. And you're going to have to do those calculations. Okay. All right, so here, I want you to practice. So I pulled out phosphorus, sodium, and copper from the periodic table. These are the exact elementiles that you'll look at. So do the math and then go online and just type in number of neutrons in phosphorus and you can check your answers, okay? But don't cheat, actually do the math out. All right. All right, oops, I didn't do this right. So the first thing I want you to do is watch this video. It's actually pretty well done. I think it does a good job of explaining isotopes. And so I want you to watch it. I'm not going to play it in this video just because that seems crazy. Oh, wait a minute. No, I have to, don't I? All right. Okay.
All atoms of a particular element have the same atomic number. This means that they all have the same number of protons. But sometimes you can find heavy atoms of a particular element. These atoms have a higher mass number. The mass number is equal to the number of protons plus the number of neutrons. We can ignore the electrons as their mass is so tiny.
So keep in mind that In this video, they're showing the mass number as something that shows up on the periodic table. The periodic table we're using doesn't, but just so you understand the difference between what she's saying and what we talked about a few minutes ago.
If the number of protons always stays the same in a particular element, and we are ignoring the mass of electrons, it must mean the number of neutrons is causing the difference in mass. Atoms of the same element with a different mass number are known as isotopes. They are defined as atoms of an element which have the same number of protons but a different number of neutrons. If we look at carbon and nitrogen, are they isotopes? They have different mass numbers, but they also have a different number of protons. Therefore, they are not isotopes. They are completely different elements. Different isotopes of elements do not have separate positions on the periodic table. They occupy the same spot because they have the same number of protons. What about carbon-12 and carbon-14? Both carbon-12 and carbon-14 have the same atomic number, which means they have the same number of protons, but they have different masses. Carbon-12 has a mass of 12 and 6 protons. Remember, mass number equals protons plus neutrons. So we can rearrange this formula to give us neutrons equals mass number minus protons. 12 minus 6 equals 6. Therefore, it has 6 neutrons. Carbon-14 has a mass of 14, but it still only has 6 protons. Mass number equals protons plus neutrons. Rearrange. Neutrons equals mass number minus protons. 14 minus 6 equals 8. Therefore, carbon-14 has 8 neutrons. Carbon-12 and carbon-14 are not the only examples of isotopes. There are many more, such as hydrogen, deuterium, tritium, and chlorine-35 and chlorine-37. Isotopes only differ in their number of neutrons and their mass. Their chemical properties are exactly the same because neutrons have no effect on an element's chemical behavior. This is
Now, just to clear that up, it's true that they have no effect on the chemical's behavior. However, what they do change are nuclear reactions, which is what happens when you're involving the nucleus in the reactions, which for our purposes never happens. So that's what the different ones are used for in some other type of reaction or calculation. So we don't have to worry about those.
controlled by electrons, which we will discuss in another video. So isotopes are atoms of the same element with the same number of protons but a different number of neutrons. They have different masses, but their chemical properties are exactly the same.
Okay. So let's go back to here. Okay, so this is just a summary of some of the things that hopefully you got out of the video. All right, so here is another representation of carbon. I just thought it was nice and clean with everything on the same page. And if you count them, you can see that the protons, which are the orange, are always 6. But the neutrons differ, and therefore they have different mass numbers. But the mass number that you calculate from the periodic table is always, always, always the mass number of the most common isotope. And I'm telling you right now that the most common isotope of carbon is carbon-12. Anyway, let's take a look at that. Okay, whoops, I didn't put any animation in this. So the atomic mass is not a whole number because it's an average of the isotopes in a sample of the element. Now, when calculating that average, some chemist along the way, or many chemists along the way, figured out how frequently different isotopes show up if you take a sort of general random sample of carbon. So looking over at that table, carbon-12, which is the most common, shows up 98.9% of the time. Carbon-13, only about 1.1% of the time. And then carbon-14, PPT means parts per trillion, which means it's very, very rare. But if you use weighted averages, which some of you may or may not know what that is, and it doesn't matter. if you calculate weighted averages, it comes out to be 12.011 AMUs. And if you check the periodic table, you'll see that the atomic mass of carbon is 12.011. I did show the math for this on a video in Schoology. You are by no means required to know how to do this, but if you're interested in the math, please take a look at that, okay? All right, neutral. I love this. So getting a little punchy last night when I put this together. So a neutral atom is found in the neutral zone. The number of protons equals the number of electrons. Neutral means that it doesn't have a charge. And if the number of positive charges equals the number of negative charges, then they kind of cancel each other out, and it becomes the overall net charge is zero. There is no charge. And hopefully you got that out of the PhET that you did. So a neutral atom, it's logical, knowing what you know about the word neutral. So hopefully that'll help you remember, and you can picture some sort of Romulan Federation standoff when you do that. All right, and the last one, stable atoms with filled outer s&p orbitals. Now you say, Millender, I don't know what that means, and that's fine. Do I need to know this right now? No. So again, it's late. I'm getting punchy. And so that is the end, and hopefully you learned a lot, or at least review some stuff. Thank you very much.